So, okay, what are the instructions? Only one answer per question is allowed. For each question, completely fill in the circle alongside the appropriate answer. Okay, so I'm just going to be using a highlighter in this case, but actually in your real exam, you do need to circle it out in blank ink. Okay, so do remember that, very critical. I'm just going to be using a highlighter here in this video. However, in your exam, you do need to circle this like the instructions have said clearly in black ink. Okay, so question number 3, which of these elements has the second ionization energy? Now, if you look at the periodic table, sodium is to the far right. So that means on top of that, it has a very low atomic proton number. So that means that sodium is going to be having the highest second energy. Okay. Question number 4 is, which of the following shows that chlorine in its correct oxidation states in the compounds shown? So what we're going to do is we're going to check each one accordingly. Let's actually look at option. Okay, part 1. Remember, the total, okay, we have to find out the oxidation state. The total oxidation state of hydrochloric acid is actually 0. For KClO3 is also 0. For HClO is also 0. For HCl is also 0. That's a total oxidation state. The charge is 0, and the state is 0 in that case. However, for chlorine, right, it's going to be -1. So it's -1. That's right. For potassium, if you look at the periodic table, where this K is actually +1, plus that it's going to be the oxidation state of chlorine is +1. For oxygen, the oxidation number is going to be -2, so it's going to be 1 plus chlorine, 1 plus 3 times -2 equals 1. 1 minus is going to be chlorine is going to be that -5. It's going to be +5 for chlorine. So this is not it. This is not it. This is it. This is it. Okay. Remember, it's -1, so that means this is not it. So assuming, since you got 2 of these right, this is going to be your final answer. It's going to be option C. So you can really guess and like actually solve this immediately. So it's for C. That's going to be your answer. Which of the following contains the most chloride ions? You can actually use this to calculate the number of moles. That's a good solution. So in this case, if we do 3.30 times 10 raised to the power -2, and we multiply it by 10 divided by 1,000, that's going to give you a value of, this is going to be 3.3 times 10 raised to the power of -4. You do the repeat step again. 5 times 10 raised to the power -2 times 20 divided by 1,000, it's just going to give you 1 times 10 raised to the power -3. You do the same thing again right here. -2 times 30 divided by 1,000, which is going to give you 9.9 times 10 raised to the power -4. Do the same step again. You're going to get roughly, okay, 1 times 10 raised to the power 3. Now we know the number of moles. We're just using that same formula over here. I'm just going to show you guys. We're using this formula over here to calculate the number of moles. Okay. So using that, we're calculating the number of moles, and now we're going to check which one has the most number of chloride ions. So in this case, you know that -3 is greater than -4, so that means you're going to, no, it's not this one, neither is it going to be this one. Actually, calcium chloride and sodium chloride, actually they have the same number of moles. So how do we know which one has the most chloride ions? Now we're going to be looking in terms of the I'm just going to put this brackets just to confirm if it's the same value. If it is, that means then we have to make it out in terms of which one's bigger and smaller. So calcium is over here, sodium is over there. Calcium has a higher atomic number, whereas sodium has a smaller atomic number. So that means your answer is going to be part B, calcium, because it has a higher proton number. Okay, so yep. So it's 5B. Next question, part 6 is, this one shows a Maxwell-Boltzmann distribution. You can see the number of molecules. What does the area under the curve represent? So it represents, actually, it's not the total energy of particles, neither is it the number of particles that can react, nor is it the total number of particles that have a high activation energy. It is actually the total number of particles. So it's going to be 6B. Okay. Next question. The apparatus in figure 2 was set up to be shown to react with that much amounts of hydrochloric acid, conical flask, the timer, longer possible. What's likely to decrease the accuracy of the experiment? It's actually going to be the if you read this carefully, it's going to be 7 rinsing the flask with acid, stirring the solution, using the same piece of paper. Using the same piece of paper for each experiment is not related to the accuracy of the experiment, actually, because it's doing a good job. Using different measuring cylinders to measure volumes, it's also not going to decrease the accuracy. However, rinsing the flask with acid before, yep, that's going to affect the accuracy of the experiment. So it's 7A. Okay, question number 8. The experiment was repeated at 20 degrees Celsius. Using that much Wood's statement is correct about time taken when using a larger conical flask. Time taken will not be affected by a larger conical flask. That's not right. Time taken will be decreased by using a larger conical flask. Nope. The time taken will be increased by using a larger conical flask. Yes, that is the right one. Because as the size of the conical flask increases, the time will also increase. So it's going to be 8C. Question number 9. Which change requires the largest amount of energy? Now look carefully at the charges. Okay, the first ionization energy and the second ionization energy. You can check that, and this is how you differentiate. So it's going to be actually, now you can see that lithium is showing the first ionization energy, and sodium as well, whereas helium and magnesium are showing the second ionization energy. So in terms of this, helium has a lower atomic proton number than magnesium, so that means it's going to be 9A. Okay. A sample of 2.8 grams of oxygen has a volume of that much at a pressure of that. What is the temperature of gas? This is using the formula of PV equals nRT, I think. Yep, it should be using that. We have to calculate the temperature, so you're just going to be doing a bit of rearrangement. So temperature is equivalent to PV divided by nR. They've given you R, which is the gas constant. So on top of that, pressure in kPa. We have to convert 1 kPa is 1,000 Pascal. By the way, we have to convert the pressures On top of that, we have to convert this. We're going to use this over here. We have to convert cm cubed to meter cubed because volume is measured like that. So we're just going to zoom in. Change the values first. Really important that you change the values. So 101 kPa, you're going to multiply it by 1,000 pascals. So the pressure is going to be 101 times 1,000, which is going to give you 101,000 pascals. All right, so that means the volume, we have to also convert it to 1870 centimeter cubed. You're going to divide it by 1,000, which is going to give you, careful by the way, 1.87 dm cubed, which you're now going to divide it by 1,000 to give you, in terms of meter cubed, 1.87 times 10 raised to the power negative 3 meter cubed. Okay, meter cubed. I'm just going to resize this so that the size, so that we have more space to show a good amount of working. So yep, just gonna resize this. Maybe I just need to move this to the other side. Okay, all right, now we've converted the values. Now all we just need to do is substitute pressure 101,000 pascals, multiply it by the volume 1.87 times 10 raised to the power negative 3 meter cubed. Number of moles, apparently this requires a little more calculation. They've given you a sample of oxygen gas, so we have to actually now use the other formula over here, this triangle here. I'm just going to be showing you, it's over here. Okay, so we have to calculate the number of moles. So number of moles of oxygen is going to be 2.18 grams divided by the MR of oxygen, which is here is relative atomic. Here it would be 16, so that means it's 2.18 divided by 16, which is equivalent to 2.18 divided by 16, which is going to give you 0.13625 moles. Okay, you're now going to substitute this value over here. You're going to multiply it now by R, which is given to you as 8.31 joules per Kelvin per mole. Okay, quite a bit of calculation for a wind marker. I'm surprised, actually, with the amount of working that you have to do to show your steps. Very important. Now what you need to do is just substitute this into your calculator to get it in terms of, how do you say? In terms of temperature, which is in, I'm assuming in kelvins. Yep, it's in kelvins. 13625 times 8.31, that's going to give you roughly 166.18 kelvins. So if your rounded temperature is 167 kelvins, it's going to be 10. Oh yeah, sorry guys, by the way, be very careful. Remember, this is oxygen gas. Okay, this is oxygen gas, so that means it's going to be O2. So you're actually going to be doing 2 times the MR, or whatever, 2 times the MR. Okay, you're going to be doing 2 times the MR because there's 2 oxygens. So your value is going to completely change. It's not going to be this one. So because it's an oxygen molecule, you're just going to do it as 2.18. Really careful with that because oxygen is O2. 2 molecules of oxygens are there, so it becomes 0.068125 moles. Now we can substitute this into our equation over here. Just gonna put it here. Yep. So like that, be really careful when putting answers like that one. Okay, now I'm just gonna substitute it back again. Yeah, I'm just gonna substitute it now forward again. Now the value is completely different. Yeah, so now I'm just gonna substitute it forward again, and that's gonna give us 333.6 kelvins, which is going to give us 334 kelvins. This is going to be your final answer. It's going to be actually 334 kelvins. 10B is going to be your answer.